Can a small aerofoil-shaped device like this revolutionize aviation safety? And if so, how? Aircraft stalls, as in where an aircraft wing or its stabilizer exceeds its critical angle of attack and effectively stops producing lift, is thankfully incredibly rare in commercial aviation. But they do still happen, and we saw a very tragic example of that not too long ago with the loss of WEPA's Flight 2283. Now, airframe icing is often found to be a factor in these type of events, even though stalls can happen for other reasons too, and they can be quite hard to predict, especially when icing is involved. But what if we already have the technology needed to avoid these type of events? Why wouldn't we use it? Good decision making always depends on having the right information, since that helps dispel confusion during stressful situations and can therefore stop an accident sequence from becoming fatal. So what we are going to talk about today is exactly that. A way for us pilots to get the right information about what our aircraft is doing and how we need to react in response. Now, we recently made a video about the Lockheed C-130 and how it is possible for an aircraft that had entered service in the 1950s to not only be still in service, but actually still be in production over 70 years later. And while we were researching that video, we found an interesting anecdote about its development, which is very relevant to today's story. You see, in the 1990s, Lockheed was testing out the newest version of the C-130 called the C-130J. This J model had new avionics and no flight engineer in the cockpit, but most importantly, it also came with a new set of engines and propellers. Now, when Lockheed's test pilots first flew this new version, they discovered that it had a strange issue. For some reason, it initially refused to stall at the speeds where the previous models would definitely have done so. So the test pilots therefore ended up flying the aircraft just slower and slower, expecting it to give them some type of light buffet in the controls, which usually is what warns us pilots of an impending stall. But instead, they got nothing. Now, that might sound like a good problem to have, but actually it isn't, because when the test crew then flew even slower than that, the aircraft eventually stalled very suddenly and without warning, whilst also doing a snap roll, something that is extremely dangerous in an aircraft like this. So what was going on then? Well, it turns out that those new propellers with their 6 blades were cleaning up the airflow over the wing a little bit too well, and that meant that the airflow on the upper side of the wing remained attached for longer, effectively delaying the stall. But like that snap roll had showed them, this also made the plane's behavior less predictable once it slowed down, and that was something Lockheed couldn't ignore, since handling characteristics like that could cause the aircraft to enter into an uncontrollable spin. Now, addressing this problem took some time, which added significant delays to the C-130J's program, and in the end, Lockheed decided to just fit a stick pusher to it to keep its crews from slowing down to unsafe speeds. And to really understand why this is so important, we need to talk about how wings work and how we pilots keep track of how well our aircraft are flying. In simple terms, the air flowing over an aircraft wing's curved upper surface will accelerate to a speed that's higher than that of the air on the underside of the wing. And that speed differential means that a low pressure will be created on the upper side of the wing and a high pressure on the lower. This, together to some extent with Newton's third law of motion, creates the lift that we use to keep our aircraft flying. Now, I am simplifying things a little bit here, because in reality some people are still arguing that we actually don't really know exactly how wings generate lift, but that's a whole other discussion. What I want to focus on here is actually what happens to the airflow over the wing when it's subjected to a higher angle in relation to the oncoming air. That angle, specifically the angle between the wing's chord line and the oncoming airflow, is what we refer to as the angle of attack. And we measure this using something called angle of attack sensors, or vanes, which on most modern airliners are basically short metal vanes that stick out from the side of the fuselage. A little bit like weather vanes, but installed vertically instead of horizontally. Now, as the wing's angle of attack changes and the oncoming air changes direction, these vanes then swing up or down, and their position is continuously recorded internally to give us the correct angle of attack. There are generally 2 or more of these, usually located near the nose of the aircraft, not on the wings, and that's worth remembering. So, as Ben explained in a recent video, as the angle of attack increases, the amount of lift that the wing produces then increases, until the smooth airflow on the upper side of the wing becomes turbulent and eventually separates. When that happens, the lift that the wing can produce drops really quickly, causing the aircraft or the wing to stall. Now, one reason why the wing might be using a high angle of attack is because the plane is flying really slowly, but it is not that simple. The aircraft could also be in a steep turn, or its crew could be pitching sharply upwards, both of which could cause the effective weight component pulling on the aircraft to increase. Now, you might have heard of this as the aircraft is pulling a lot of G's, with 1 G being equal to the Earth's gravity. And if the effective weight is higher, then the wing needs to produce more lift to compensate, which leads to a higher angle of attack. Again, it is a little bit more complicated than that, but I hope you understand what I mean. Anyway, this is where we get to an issue that is a little bit of a hot topic among pilots, especially when the pilots are coming from different backgrounds. In the airline world, we typically keep the aircraft safe by referencing mainly to our airspeed and attitude. We pilots and the aircraft manufacturers know what speeds we should be using for each phase of flight and configuration, and our primary flight displays include symbols on our airspeed tape that tells us what speed is too slow for the current flap configuration, for example. But of course, those speeds assume that we aren't making very sudden maneuvers or very steep turns, which would increase the G load on the wings. But even if we would do that, modern flight displays will react and warn us for that as well. So pilots with a civilian background are often quite happy with just these type of indications. But on the other hand, pilots with a military background generally prefer to have a direct reference to the angle of attack instead of just to the airspeed. And that's since, as many of them often point out, a wing can stall at any airspeed, but will only stall at one angle of attack. Now, the reason a lot of military pilots in particular think this way is because many military jets, like fighters for example, operate at much broader speed ranges than airliners do. But more importantly, they are also flown more dynamically, by pulling Gs for example, which pose even greater demands on their wings and can increase the angle of attack very, very suddenly. And also on top of that, fighters tend to have much simpler and less effective flaps and slats. Now, that might not apply to all military jets, or at least not to the same extent, but it is important enough that military pilot training generally puts a lot of emphasis on referencing their angle of attacks, which is why airline pilots with a military background still tend to value angle of attack considerably more than other pilots do. This is actually so prevalent that in aircraft like the Boeing 737 that I fly, an angle of attack indicator is available as an option for their primary flight displays. And airlines that have a lot of former military pilots in their rosters always tend to pick that option. But is it actually true that an angle of attack indicator always tells us what our plane's wings are really doing? Or to put it another way, do wings really stall at only one angle of attack? Well, technically, yeah, they do, under normal circumstances, which actually doesn't say much since we don't design aircrafts and their systems or our procedures to operate only under normal circumstances. Now, I'll get back to what I mean by that in a second, but it actually brings me to a really important point. You see, researching these kind of videos requires a huge amount of work. My team and I need to jump between technical manuals, articles and expert interviews, and that can quickly lead to just too much information. And that's why I have started using today's sponsor, the Plod Note Pro, as my professional research partner. Now, this is an AI note taker that's truly multimodal. So when I'm researching a complex case, like I did in a recent video about an MD-11 accident, I can use it to record audio, snap photos and jot down notes simultaneously. And if I hear a critical detail during an interview, I will just press a button to highlight it, and the AI will note the 30 seconds before and after to make sure that nothing gets missed. Claude then turns everything into clear summaries, a mind map to visualize the logic, and a to-do list for next steps. And there are over 7,000 templates for different professional uses. Now, one of my favorite features is the Ask Claude, where I can ask things like, what was the key issue with the MD-11? And then instantly get an answer based on an over hour-long interview with an expert. On top of that, the hardware in itself is really impressive. With an AMOLED screen, 4 built-in microphones for clear recording, and over 50 hours of continuous recording on a single charge. And Claude also meets strict global privacy standards like SOC 2 and GDPR. So, to learn more, scan this QR code or check out the link below in the description. It is really useful. Thank you, Claude. Now back to the video. So let us now look at the angle of attack a little bit more closely. Like I already said, any given wing will always stall at the same angle of attack, called the critical angle of attack. Except when it doesn't. If the wing would be contaminated, for example, well then the airfoil will basically get a new shape, effectively causing it to behave like a completely different wing. And depending on the type of contamination, it could therefore stall at angles of attack that vary by as much as 6 degrees away from what would be expected. This could also happen if, for some reason, the wing is at a different configuration than it should be, meaning if the flaps or slats, or maybe even both, aren't where they're expected to be, because that would effectively, again, be a different wing with a different critical angle of attack. The same also goes for an aircraft that is flying in the ground effects, where the angle of attack could vary by a couple of degrees or so. And on top of all of that, there's also something called stall hysteresis, which basically means that after the wing have stalled and the pilots push the nose down in order to reduce the angle of attack and then recover, the airflow won't simply reattach itself to the wing when the angle of attack returns into the normal range. Now, in reality, the angle of attack may need to be reduced even further, often another 5 degrees below the critical angle of attack, in order for the airflow to resume. And that matters, because in a scenario like that, when the pilots begin to recover, the stall warning might initially stop activating at a certain angle of attack, leading the pilots to assume that the plane is no longer in the stall, which won't necessarily be true. Then there are also other, more technical reasons why the wing might stall before or after the angle of attack that the pilots would expect. A failing angle of attack sensor, for example. Now, of course, modern aircraft have safeguards like redundant sensors and other systems to warn us if our data isn't reliable, but for some situations, like that post-stall hysteresis, for example, redundant angle of attack sensors won't really help, since they will all be reading the same angle of attack, but without telling us the whole story. So the whole point that I'm trying to get to here is that even though angle of attack is a very useful parameter to help us determine if a wing is about to stall, it is only a proxy parameter. It doesn't directly tell us what the wing and the airflow around it is actually doing, especially if the wing is contaminated. Now, in the vast majority of cases, with redundancy, anti-ice and de-icing procedures, the angle of attack information is absolutely fine. But the thing is that there is a direct way to actually see what the wing is really doing. And at least for test aircraft, this is far from a new idea. You might have seen videos of aircraft being tested with banks of strings or tufts attached to the top surface of the wing to visualize what the airflow looks like as the aircraft flies at higher and higher angles of attack. As that happens, the turbulent layer at the back of the wing will start to move forward, and you can see how those previously straight tufts then start swirling around in the now turbulent air. Well, what if we could put something else on the top surface of the wing permanently to provide us with similar information as that? Would it be possible to use something like that to replace or at least complement the angle of attack sensors? This finally brings us to the device that I want to look at today, the Airfoil Performance Monitor, or APM. Now, I should make something completely clear before I go any further. This video is not sponsored by Marivent, which is the company that's developing APM. We have been in contact with them, and we've done so for the last couple of weeks, and they have provided us with some more information, including testing results that we were able to verify with the help of others in the industry. But we have chosen to showcase this system here because we thought that it deserves more exposure among other innovations and solutions that could potentially save lives. The APM sensor sits in an aerodynamically shaped housing, and it's designed to be placed on the upper side of the wing towards the rear. The sensor then has two orifices or holes at the front, plus one opening in the rear that serves as a static port, and on top of that it also has electrical heating to keep it from freezing over, as well as a drain hole to get rid of any water that might have gotten itself inside. Now, the reason that this sensor needs to be located far back on the wing is because at high angles of attack, that's where the airflow begins to separate. So in flight, air flowing through the two holes in the front of this unit is used to determine what the company calls the turbulence intensity parameter. This is defined as a ratio of the turbulent airflow component to the mean airflow velocity. And in simple terms, that means that the turbulence intensity tells us how disrupted the airflow is over the wing, and therefore how close it is to stalling. And then several of these devices can be placed on the wing if it is necessary. Now, this isn't a new idea. In one form or another, APM has been in testing since back in 1979, and it was actually test flown for the first time in 1984. Since then, it has been worked on in several wind tunnels, as well as being flight tested in aircraft as varied as the Grumman AA-5, the Lockheed T-33, the Piper PA-30, the Cessna 421, the ATR-42 and 72, and the Fokker 100, among others. In previous years, the company that developed the system licensed it to BF Goodrich, who planned to market it as Stall Warning Plus. But according to the company, those plans then fell through after 9/11, when the industry went into crisis mode and any investment of new safety systems became a very low priority. So the technology then reverted back to the patent holder, which is Marivent in Canada. Now, in testing, this device has demonstrated that when the aircraft has an uncontaminated wing, the turbulence intensity information that it generates is consistent with angle of attack information. But the really interesting part is what happens when the wing is contaminated. Again, that would usually be due to icing, but it could also be from dirt, loads of dead bugs, or even structural damages like dents. Unlike the angle of attack data, which wouldn't change at all with contamination, the APM sensor shows the turbulent airflow that the contamination causes. So, in practice, the aircraft systems would then be programmed to warn pilots about an impending stall at a given value of turbulence intensity, instead of at a certain angle of attack. This means that if an aircraft would be flying with a dirty or contaminated wing, that turbulence intensity would increase earlier, and the pilots would then be warned about it. Now, that alone makes this device really interesting to me, but it also has a couple of other tricks up its sleeve. You see, that same early warning about high turbulence intensity would also be given in other conditions. For example, if the aircraft's flaps and slats aren't configured properly, causing the airflow to start separating earlier than programmed during a takeoff, for example. And another really neat trick is that the APM can tell us that the wing is contaminated before rotation, while we're still accelerating at relatively low speed during takeoff, and that is a really big deal. You see, sometimes, luckily very rarely, mistakes can be made during the de-icing procedure, or the icing could be mistakenly skipped, or the fluid could be, outside of its effective time. But when we're on the ground and rolling for takeoff, because of the nose-low attitude of most aircraft, the wing won't really be starting to work until we try to rotate. So our usual sensors can't really tell us if anything is wrong until we reach that point. But since the APM sensor monitors airflow continuously, if there is contamination over the wing in front of the sensor, it can detect that, at airspeeds as low as 55 to 80 knots, which is low enough to allow us to then safely reject the takeoff when we get the warning. Also, remember what I said earlier about what happens to a wing after a stall? Hysteresis? Well, just to recap, once the airflow is detached from the wing in a stall, the angle of attack might have to be brought much lower than the point where the wing stalled to get the airflow back in place again. And normal angle of attack indications can't offer much feedback on when that actually happens. But by contrast, the APM sensor will track the return of normal airflow over the wing exactly when it happens. So pilots won't need to guess when their wings are working properly again. More generally though, when the information from the APM sensor is combined with that from an angle of attack vane, pilots can get feedback on wing contamination as they fly, and if needed, APM can then also be used to verify the function of other sensors. This system could also be really useful for pilots of unmanned aerial systems, like big fixed-wing drones, for example, because the pilots that are operating those don't really get any seat-of-the-pants feedback, like pre-stall buffet, for example, so APM could potentially fill in that void. But by far, the main benefit of this system, from my point of view, is how it could help pilots handle an aircraft that is unintentionally flying in icing conditions. The reason that this, and wing contamination in general, are such big threats in aviation is precisely because they can undo many of the protections that our aircraft are built around. So a system that directly measures and tells us what our wings are doing, independently of other existing safeguards, is just a really, really interesting idea. Now, in the end, I want to get back to where I started this video. Good decision making is made possible by giving pilots the right information when things go wrong. And any system that can provide us pilots with more nuanced and earlier information is definitely worth pursuing. And I think that APM might be one of those. Now, we would like to start making more videos like this, showcasing innovative ideas that could make aviation safer. So please let us know if you know of any other serious candidates for this, and also let us know what you thought about this one. Did we miss anything? I also want to take this time to highlight some of the best and most heartwarming comments that we received on our last video. Please know that we love hearing from you guys, and we take your comments very, very seriously, so please continue sending them in. My team now consists of around 15 people at any given time, working across all of our different channels, and that's only made possible thanks to our fantastic sponsors, as well as my awesome Patreon crew, some of whom you can see scrolling by right now. Now, if you want to help our mission to make aviation safer, then please scan this QR code or go to patreon.com/join/mentorpilot and sign up. My name is Peter Hörnfeldt and you're watching Mentor Now. Have an absolutely fantastic day and I'll see you next time. Bye-bye.